All right, folks, so let's get started. We will finish chapter 6 today, and then any leftover time today and Wednesday, we will do midterm 2 review. So remember that I have a Zoom session on Wednesday. Did any of you guys go to the review session over the weekend? Okay, some of you, cool, awesome. Hopefully that was useful in reviewing some of the plentiful midterm materials we have. All right, so let's get started with where we left off. We were talking about atomic orbitals, all right? So this is a consequence of solving the Schrodinger equation. Well, we never solved it, okay? We never solved the Schrodinger equation, but what we learned, what we got out of the Schrodinger equation and application of Heisenberg's uncertainty principle, we can't know the position and the velocity or the energy of an electron both precisely simultaneously. So that gives us our orbital shapes. These shapes are a consequence of a fairly large delta x, uncertainty in position. And those are the shapes that we talked about, those quantum numbers. So these are the shapes of the orbitals, and I have them up here too, and I'll show you. So we talked about the rules with quantum numbers. Our n value, same type of energy level idea as the Bohr model, but now we've introduced our L quantum number. This tells us our orbital shape. Our m sub L quantum number, that tells us our orientation, or how many atomic orbitals are within one subshell or one shape. And then we have our spin quantum number. So putting all those ideas together, we see our different orbital shapes. All right, so let's remind ourselves, our L quantum number, this is our, this tells us our shape. All right, so this number also tells us the number of angular nodes in that shape. So you can see when we have 0 angular nodes, we get this spherical shape, all right? We have a perfect sphere here, and so what you see are sphere and then these like metal rods, that's like our XYZ axis, all right? And so, you know, based upon your L quantum number, you can predict your possible M sub L. So for an L equals 0, what are our possible M sub L quantum numbers? Only 0. So that means an M sub L of 0 means, or like that the only possible one is 0, is that there's only one orientation possible. Because if we think about it, if we kind of change this sphere in 3 dimensions, it doesn't really change what it looks like in a XYZ coordinate system. So what you see here, there's only one unique orientation for an s orbital. And so how I like to think of it is if we're thinking about an s orbital, we have one box. There's only one specific orbital that we can have, and 2 electrons can go in that box. So over here, I kind of copied the energy level diagram of a hydrogen atom. These boxes that I'm drawing are the boxes that you see here. So this 1s box, that box has a shape of this spherical shape that you see here. All right, and so then our next quantum number that we have here, our shape is our p orbital. And so what you see here, what are our possible m sum l's that we can have for L equals 1? 0, or well, I usually start the negative side. So -1, 0, +1. And so that's why there are 3 unique shapes. -1, 0, +1. They're all different possible quantum numbers that we can have. And so that's what you see here for our p orbitals. This is a little harder for me to kind of demonstrate. So there's 3 unique orbitals that you see here. We can have our dumbbells align on the z-axis, so up and down, or we can have it align on the x-axis or the y-axis. So each one of those shapes corresponds to a different ML or orientation quantum number. And so how I usually like to represent it is as 3 boxes. So you can see 3 boxes, 3 orientations is a p-type orbital. And so this could be like 2p or 3p, depending on what energy level we are in. And so now you kind of see the trend, right? For a d orbital, or L equals 2, we have 2 angular nodes. So we have more lobes in our shape. This is the butterfly shape. And so what we can do is change this butterfly shape in 3 dimensions. Okay, we can have unique shapes in 3 dimensions. So if we think about our possible m sub l's for this L value, we can have -2, -1, 0, +1, +2. That's why we have 5 different shapes. So you can imagine we can have 5 different boxes for a d orbital. And then the same thing for our f orbital. We don't really think about f orbitals too often. All right, and there would be 7 boxes or 7 different unique orbitals, and I have those shapes here. So you can see there's 7 different orbital shapes with our orientations. All right, so this is an F orbital where there are 2 angular nodes, and I think one of our classmates described what an angular node is. It's like taking a balloon and twisting it, and how many times you twist it is what that orbital shape would look like. So for example, an s orbital, if you take a balloon and do you have to twist it at all to make a balloon look like this? No, so that's why L equals 0. You don't have to twist it. But if we take a p orbital, all right, and if we wanted this balloon to look like this balloon, how many times would you have to twist it? Just once. If you like twisted it in the middle like a, like a balloon animal or whatever, then you could get the shape that looks, yes, those you. You could get it to look like this. So this, you would twist it once, so L equals 1. And then if we move on to our d orbital, it looks like a butterfly, all right? So then we have more angular nodes or nodal planes, so you have to twist it twice to get this many like lobes on your balloon animal, and then so forth, okay? And then a bunch of lobes on the f orbital. All right, so these shapes, these number of boxes translates to this idea of our energy levels for our hydrogen atom, all right? And so all of those are related in that way. And I like to remember, okay, the number of boxes, those are the number of possible M sub L's, 2 electrons in each box. How do we get 2 electrons in each box? Yeah, one has to be spin up, one has to be spin down. All right, so let's go into details about the orbitals. All right, so you can see there's a couple different ways that we can represent orbitals. So we'll go in order here and talk about our s orbital. So we talked about the shape, that it's completely spherical, meaning that the probability of finding an electron in an s-type orbital is in this spherical shape, some certain distance away, some certain radius away from the nucleus. So there's a couple different ways we can show it, like in this picture. These are just possible places you could find an electron. So they kind of have it like in this dispersed kind of graph, or we can show it as a contour model showing you, okay, 95% of the time you will find the electron inside this volume sphere here. Another way we can describe finding an electron is with a radial probability function. So how this graph works is if you think of an orbital, and remember all these orbitals represent the probability of finding an electron, pretend you are the nucleus, pretend you are the nucleus. And you start to walk out towards the nucleus, so you like extend your radius out, and you plot the probability of finding an electron a certain radius away from the nucleus. So maybe another way to describe this type of graph is to think, okay, right here, this is the nucleus. Okay, the front of the room is the nucleus, and all of you guys are electrons. Okay, so if I plot the probability of finding an electron as I move away from the nucleus, all right, so I'm at the nucleus and I'm increasing my R, all right? So right now I'm not finding any electrons, but now that I enter the space where there are electrons, the graph goes up, right? Electron, 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 electron. So the graph is going higher and higher and higher. I can find lots of electrons because you guys are electrons. But then once I go to the back of the room, do I find many electrons back here? No, so then the graph goes back down. So what you're looking at, or what I just described, is that first graph on the left, all right? That first graph on the left is showing the radial probability of finding a 1s electron. So a electron that is closest to the nucleus in its 1s energy level. So that's kind of what we see here. If we are right at the nucleus at a distance of 0, we won't find any electrons. But as we start to increase our radius out, we have a higher probability of finding an electron. But then once we get far away enough, we don't find them anymore, all right? So this is for a 1s electron. So what happens when we increase the energy of the electron to, let's say, 2s, you kind of get these shells, all right? A 2s electron is slightly further away from the nucleus. So that's kind of what you see here, but you still have some probability of finding that electron in your 1s, kind of closer to the nucleus, but on average, a 2s electron is further away from the nucleus, and that kind of goes with our Bohr model as well. And then if we go even higher energy, a 3s electron, you can see on average that electron is even further away from the nucleus that you see here. All right, so distance from the center, you can think from the nucleus. And this graph is just kind of plotting where will we find the electron relative to the nucleus, to the center of the atom. All right, so more details about these graphs. So here again, this is a 1s orbital, 2s, 3s. Now what's kind of interesting is what we like to think about and where the idea of quantum numbers comes into play is every time the graph goes to 0. So note in our 2s radial probability graph, see how this graph goes to 0 at some point, right? It goes to 0. So the idea that the graph goes to 0, that as we're going away from the nucleus, we find an area of high concentration of electrons, but then none, and then high again. That idea is basically based upon the Bohr model, right? One of the tenets of the Bohr model says that you can't have electrons between energy levels, right? They have to be at certain, like n equals 1, n equals 2. So there are these regions where you don't find any electrons, and that is consistent with the Bohr model. And so when the graph goes to 0, we call that a node. All right, so this right there in this 2s graph, this is a node. So this graph has one node in it, specifically one radial node in it, because it's a point where the graph goes to 0 on the radial probability graph. So then if we look at our 3s electron, the graph actually goes to 0 twice. So there are 2 radial nodes within this graph. So note here, I am not counting the beginning or the end of the graph. I don't count these zeros. I only count the times the graph goes to 0 kind of in the middle there. All right, so what we see here is that our 1s electron has no radial nodes within it. So there are no points where the graph goes to 0 because we're not counting the beginning and the end. So how radial nodes relate to our idea of quantum numbers is that's how we essentially calculate our orbital size. Is depending on the number of radial nodes and angular nodes within a certain orbital set of quantum numbers. So I have those definitions here. It's all based upon angular nodes and your principal quantum number. So your number of angular nodes, do we recall, how do we figure out the number of angular nodes in an orbital? It's the L value, whatever that is. So in let's say a 2s orbital, how many angular nodes are there in a 2s orbital? S is an L equals 0, so in that case there's 0 angular nodes. So then how we get the number of radial nodes is we take the n value, we subtract the L value, and we subtract 1. This is how we can calculate the number of radial nodes for a specific orbital. So for example, let's just do it for 2s. In a 2s orbital, what is n equal to? 2. What is L equal to? 0. So a question can say, how many radial nodes is in a 2s orbital, and then how many angular nodes are in a 2s orbital, and how many radial nodes are in a 2s orbital. So you can just take these equations and determine that. So in a 2s orbital, there will be 0 angular nodes because L is 0. But for radial nodes, a 2s orbital will be 2 minus 1 minus, 2 minus 0 minus 1, so 1 angular node. So see how all of that comes together? All right, and so we can do this for any orbital. All right, you can do the same calculation for a 3s orbital. 0 angular nodes, but then if we count the number of radial nodes for a 3s orbital, it's 3 minus 0 minus 1. So there should be 2 angular nodes in a 3s orbital. Do we see that in this graph? Do we see 2 radial nodes for this 3s orbital? Yes, we do. All right, so the equation here works. It works, all right? Okay, did I answer all these questions? Yes, so we see on average, as the energy of the electron increases, on average, that electron's further away from the nucleus. And then this question, why do all the graphs start at 0? Like right here, why does this graph start at 0 probability, 0 probability, 0 probability? Yeah, so you're saying the zero probability at the nucleus for an electron. Yeah, you can't have an electron in the nucleus, right? Because what lives in the nucleus? Protons and neutrons, so no electrons. Yes, very good. Very good. Okay, so that is an s orbital. Now let's look at a p orbital. All right, so we have one angular node, right? Or the number of nodal planes here is 1 because L equals 1. And here are our shapes. So kind of some details about that p orbital, because we have 3 different orientations. We can name them based upon the axes each of the lobes lies on. So this is what we call a pz orbital, because the lobes lie on the z axis. This is a px orbital, and here's a py orbital. So we have 3 different unique orientations. Those represent each of your possible ml values within there. So let's look at this radial probability graph, and let's say it's for a p orbital. All right, so let's think about this, thinking about the idea of nodal planes and radial nodes in relation to quantum numbers. How many nodal planes are on a p orbital? 0, 1, 2, 3, infinity. Nodal planes. Recall, a nodal plane, so a nodal plane also, it's the same word for an angular node. I like to use both words because the homework assignment, the book sometimes uses both words, but they mean the same thing. A nodal plane is the same as an angular node. It's the same thing. So let me ask this again. How many angular nodes are on a p orbital? 1, because L equals 1 for a p orbital. So just 1. So let's look at this graph. How many radial nodes does this graph possess? What? 0. Yes, it's 0, because again, we don't count the ends. We only count the middle. So then let's predict this. Would this radial probability graph be for a 1p orbital, a 2p, or a 3p? Discuss it. Why don't you think about it and then discuss it? And remember those 2 equations. Remember there's 2 equations to calculate this, right? Angular equals L, and then radial nodes equals N minus L minus 1. So is it 1p, 2p, or 3p? Yeah.
How do you get the boxes that we do?
It's the number of shapes that we have, the number of orientations. It's m sub L, the number of m sub L's we could have. Okay, so what's our answer? Is anyone really confident? 2p? 2p, yes. So that 2p is the correct answer because it's the only one that fits those equations. All right, so 2p is the right answer. It can't be 1p because that doesn't exist. We can't have a p orbital with a principal quantum number of 1. All right, and then it's not 3p. A 3p orbital actually has 1 radial node, according to this equation, where n, and so in 2p, n equals 2 and L equals 1, and that fits our whole idea here. Number of radial nodes would be 2 minus 1 minus 1, so it's 0. 0 radial nodes, it fits that graph. All right, next up, d orbitals. There they are. So let's just, relate this to our quantum numbers. How many nodal planes or angular nodes are within a d orbital? 2, yes, because L equals 2 for a d orbital. All right, and that's why we got more lobes here. They look like butterflies. And so the naming convention here is, so a p orbital kind of exists on a line, so we can name the orientation just based upon the axes it's on. But a d orbital exists on a plane, so we actually have to name both of the 2 axes that the orbital lies on. So we have some of these d orbital planes. So this one, dyx, lies, the lobes, all 4 lobes lie on the xy plane. Okay, so chemists, we kind of want it to kind of be clear and related to something in this case, right? And so the other type of d orbital, dxz, lies on the xz plane. Dxy lives on the xy plane, right? So those 3 are kind of easier to see, but then these 2, the last 2 are a little bit different. So with this orbital, it looks like our butterfly like we saw before, but because the lobes actually lie in the axis and not between the axis, it's still on the x XY plane, but because they're on actually like bisected, like they're kebabbed by the X and Y axis, we call this the dx squared minus y squared orbital. And then finally, this one, the last one that kind of looks like a p orbital with a belt on it, we call this dz squared because it lies on the z-axis, but because it's a d orbital, it exists on a plane and not an axis along the z-axis here. We call it dz squared. So that means a dz orbital does not exist, okay? Dz, just a dz does not exist. We call it dz squared. All right, so 5 different orientations that we see there. Why are there 5 different orientations? 5 different orientations that we see. Yeah, can you have an ML value of 5? Very good, yeah. So the possible ML values for an L of 2 is -2, -1, 0, +1, +2. So those are 5 possible ML values you can have, and they correspond to those 5 shapes. And that's how it is for all of these different shapes. So other ways we can ask questions, all right? So how many nodal planes, or remember, we also call this angular nodes, does a 4D orbital possess? Angular nodes. What equation relates to angular nodes? Angular nodes equals its L value. So how many angular nodes does a 4D orbital possess? 2, yes. So we didn't need the 4. We don't need the 4. It's the shape that defines how many angular nodes that are there. All right. So let's draw a radial probability diagram for a 4D orbital. So for a radial probability, we need to know the number of radial nodes in the graph, how many times the graph goes to 0. And so that is n minus L minus 1. So in a 4D orbital, what is the n value? It's what? It's 4. So n is 4 minus, what's the L value? 2 minus 1. So there will be 1 angular node. So you draw a graph that has 1 angular node in it. Okay, and so you go boop, boop, 1 angular node right there. And so this is what a 4, if we kind of sat at, so this should be distance, this is the wave function squared. You sit at the nuclei, and then you like walk away, and you would find 2 kind of pockets of electron density there for a 4D 4D orbital. All right, and then lastly, F orbitals. How many nodal planes or angular nodes on an F orbital? 3, because L equals 3. All right, and those are all of our shapes. So we see a lot more lobes within here. We're not going to go into the details of how to identify their orientation. That's not necessary. But we can explore nodal or angular and radial nodes. So how many nodal planes or angular nodes does a 4F orbital possess? 3, yes, because L equals 3. So then how many radial nodes does a 4F orbital possess? So recall radial nodes is n minus L minus 1. So it's 0. And then how many radial nodes would a 5F orbital possess? 1. There we go. And so we could draw the graphs for that too. So for that first one, for 1 angular node, it would just look like that. And then for, 0 angular nodes, it would just have 1 kind of pocket of electron density. And then the other one, the graph goes to 0 once. So this would be a radial node of 1. So that's 1, that one's 0. All right, so that really summarizes all the ideas of our orbital shapes, okay? And how our quantum numbers kind of relate to this and explain these orbital shapes. And it's all based upon the idea that we can't know the exact position of an electron. And so that's why we have to have these shapes to describe, hey, there's a high probability we will find the electron in this space specifically. Okay, so we now know what the orbital shapes look like. So let's start filling them with electrons. Okay, so recall each of those orientations, each of those shapes is a box. Okay, and we can put 2 electrons in each box. Now let's start filling them. So yeah, each box can have 2 electrons because we have a maximum. We can have, a spin up or a spin down, 1/2. Quantum number, that's kind of our 4th quantum number. Now we now know the shapes of all of these orbitals because we talked about the first 3 quantum numbers. The last one, our MS quantum number, tells us we can put 2 electrons in each box. So here are the rules for placing electrons in atomic orbitals. The first one is Aufbau's principle. That just says that when we have electrons to place, you always place your electrons the bottom up. So the lowest energy levels first, and then you start building up. That's Aufbau's principle. Okay, so you don't start filling your 2s orbital until you've filled your 1s orbital, because you want to have a nice strong foundation. You want to put electrons in those lower energy levels first completely as you start to fill up. All right, and so the next rule here to help us fill is Pauli's exclusion principle, which just says that no 2 electrons can have the same 4 quantum numbers. So in practice, and we already kind of talked about this, in practice, that just means if 2 electrons are in an orbital, one must be spin up and one must be spin down. All right, so if we had 2 of them, 2 electrons that were both spin up in the same orbital, like 1s, if we tried to name the quantum numbers for those 2 electrons, they would be exactly the same. And Pauli's exclusion principle says that that can't happen. That's why we have that MS quantum number to go down like that, so that we can have that. All right, and then the last one, this one's probably the toughest one to describe, is Hund's rule. And I feel like if you've done electron configurations, you know that you space out all your electrons first or whatever, but explaining why you do that is a little bit more difficult. So Hund's rule says that when you have larger orbitals and you're placing your electrons, you want to spread your electrons out as much as possible before you start to place them close in the same space. So in practice, what that means is when we have like a p orbital and we have a bunch of electrons to place, so let's pretend that we have to place 3 electrons in these p orbitals. You want to spread them out. You want to put them all in a different box or a different orbital first, because what we're doing then is we're spreading out the electrons. We're putting one in this kind of shape, we're putting one in a different kind of shape, and then we're putting another in a different kind of shape. We're spreading out the electrons. Because if we think about an electron, it's what charge? Negative. So if we put 2 electrons in the same space, they're going to feel a lot of repulsion from one another. Repulsion means an increase in potential energy. We don't want that. We want to stabilize our atom. So this picture I drew where I put them all in a different space or spread them out is more stable than something like this, where I have 2 electrons in the same orientation and then one over there. Where you're putting them too close to one another, you start to feel repulsion. All right, so in practice, place electrons singly before pairing them up in the same subshell. So you'll see the same thing for d orbitals as well. You want to fill up all your d orbitals, your 5 d orbitals singly before you start doubling up. All right, and I think there's like an analogy about a bus or something, but I think comparing this to potential energy and thinking, hey, you want to spread out those electrons because if you put them in the same orbital, you experience repulsion. So this is more stable, this is favorable within there. Oh, and it uses this word degenerate. So this only works for degenerate orbitals, meaning that they're all the same energy. Right, and so like our 3 different p orientations or our 5 different d orientations, all those orbitals are degenerate, meaning that they all are the same energy. All right, so those are our rules. So now let's follow our rules for writing. Did I do something wrong? Okay, let's use those rules to actually write out electron configurations and think about where we place electrons for hydrogen and for multi-atom systems. So the strategy here is for any atom, if I asked you what the electron configuration is, you ask yourself, how many electrons does that atom have? And then you follow the rules in placing your electrons. So my question, how many electrons does a hydrogen atom have? 1. Has 1. Because we're talking about neutral atoms here, so if you look at the periodic table, you see how many protons there are. In a neutral atom, the number of electrons is the same. So it's nice for hydrogen here. We only have to place 1 electron. So we follow Hund's rule in this case, and we place 1 electron. We put it in the bottommost place, and so in this picture, it's showing to put it in that 1s orbital. They just decided to make it spin down. But if you want, it would be the exact same energy. You could also put it spin up. It doesn't matter. That would be the same energy. It would be the same energy. And then we're done. Okay, because hydrogen only has 1 electron. All right, so that would be what the orbital diagram looks like, the electron diagram. We can also actually write out the electron configuration, and this is us just using numbers and letters to tell the reader exactly where to find electrons. So what orbital do we find hydrogen's electron? What orbital is that? 1s. But then how many electrons are in it? 1. So then you do a superscript 1. All right, if this was helium, there would be another electron and it would be spin up. So it would be 1s superscript 2. So you're saying, hey, there are 2 electrons in a 1s orbital. Yeah. Yes, because we have to do, so the question is, if we have to do a second electron, it has to be spin up, because what rule does that fall under? Pauli's exclusion principle. Very good. All right, so that's hydrogen, our simplest case. What about for multi-electron systems? So this diagram shows how the orbitals start to deviate from one another for multi-electron systems. Why does it look like this? It's because with multi-electron systems, so anything heavier than hydrogen, so literally everything else, there is more than 1 electron. There's more protons, there's more interaction. So it essentially really complicates the wave function, the Schrodinger equation, so much that you can't solve it anymore. And so what comes out of it are these little deviations of energy from different subshells within the same energy level. But don't fret, you don't have to memorize what this looks like. Everything you need to know is on the periodic table. Okay, and I will show you. So do note that what the energy level diagram for a multi-electron system, see how it looks much, much different than for hydrogen. In hydrogen, all of the 3s, 3p, 3d energy levels, they're the same energy. But for any other element in existence, they're actually different. So keep that in mind. All right, so let's do an electron configuration for sodium here. So it's the same strategy. Ask yourself, how many electrons are on sodium? 11. So that means we have 11 electrons to fill. Where do we start? 1s, the bottom. So we go 1, 2, 3, 4 in the 2s. Next we go to 2p, because that's the next one. So 4, 5. Where do I put my 6th electron? The next box. So I don't do that. No, right? So that's no, don't do that. You put it in the next box, then the next box. So how many is that? 1, 2, 3, 4, 5, 6, 7. 7, 8, 9, 10. And then 11. So that would be what the electron diagram would look like for sodium. So then we can also write the electron configuration. So we're telling the reader exactly where to find electrons. So we start at the bottom. So essentially you just say where the electrons are in the order you placed them. So this is 1s, 2 of them, because there's 2 electrons there. Then 2s, 2 of them. Then 2p, 6 of them. And then 3s, 1 of them. All right. So for other atoms, do we need to memorize this order? No, we don't. It's all on the periodic table, I promise you. All right, so how we can do this is from the periodic table and recognize that how it's set up are by S, P, and D blocks. All right, so here where hydrogen and lithium start, that's our S block. And as you go down in periods, hydrogen is 1s, lithium is 2s, sodium is 3s, so forth. All right, then you go to your P block. So starting at boron, that's 2p. And then aluminum would be 3p. Gallium is 4p. And then finally, our transition metals, scantium and yttrium, that's our D block. So scantium starts at 3D, yttrium starts at 4D. So how we can use the periodic table, locate what you're trying to name. So in this case, we were doing sodium. So locate sodium. And what you want to do is start at hydrogen, name those orbitals, and make your way to the element you want. So in this case, it would be sodium. And so you get the same thing. As long as you recognize that is your S block, over there is your P block, and there is your D block. And you just kind of work your way through it. So you start at your 1s. So in this case for sodium, it'd be 1s squared. So that would bring us all the way to our 2s block, which is lithium. And so we're filling that because our goal is to get to sodium. So this is 2s2. All right. And then we make it over here to boron. So to boron, to get through that, that would be 2p6. So that fills us up all the way to neon, and then we just name that one electron to tell us that it's sodium. All right, and then that's it, 3s1. This will come with practice. All right, all the information is on the periodic table that you need. You don't have to memorize the order, right? You don't have to. I mean, I see some folks, they like have this like, I don't know, it's like a mnemonic or something, but they do something like that. Do you know what I'm talking about? Like you write them all out and then you like follow this snaky trail. Okay, if you don't know what I'm talking about, that's fine. Because again, everything's on the periodic table. You don't even need it. All right, so let's do some practice. So I have lithium here for you. So again, you use the periodic table, you locate what you're trying to name. So in this case, it's lithium. So you start at hydrogen and just make your way to lithium, to that many number of electrons. So to get to lithium, we put 2 electrons in our 1s, 1 electron in our 2s. We can also use a shorthand or condensed electron configuration where we can start at a noble gas and put it in brackets. It's like a checkpoint. It's like you're playing a video game and you like load a checkpoint. So the checkpoint here would be helium, and then you can start at helium and then just count the number of electrons to the nearest to the target element that you want. So in this case, what we're saying is that, hey, helium is this inner core of electrons, all right, and that represents helium, so we'll just draw out the last electrons that are past that inner core. And we can do that for any electron configuration coming up. So let's do a couple of these. So oxygen, locate it on the periodic table. So it would be right here on the periodic table. And so again, you start at hydrogen, so 1s, 2 of them, that brings you, whoever's on Zoom, can you mute yourself? Can you mute yourself? Okay, so 1s squared, that brings us to lithium, to helium. Then we say 2s, 2 of them, that brings us to beryllium. Now we can go from boron to oxygen, and that is our 2p. So how many electrons within our 2p do we have to place to get to oxygen? 6? 4 of them, yes. All right, and so we can use our noble gas shorthand version, all right? So you can kind of work your way backwards. Look at oxygen and kind of work backwards and think, where's the nearest noble gas? It would be helium again. That would be our checkpoint. So we can write instead helium, 2s, 2 of them, 2p, 4 of them. And that would be oxygen, all right? Let's do a harder one. Let's do zinc. So locate zinc. So it's element number 30. So we'll start at the beginning again. So 1s2, 2s2, 2p6. So that brings us to neon. Oh, we got to fill the 3s, 3p. We fill it all the way up, so 3p6. That brings us to argon. Now we go to potassium. And so be very mindful of what period you're in. So if you ever forget and you want to like count what is the orbital for potassium, count down from hydrogen. And I know that hydrogen is 1s, lithium's 2s, sodium is 3s, and potassium would be 4s. So you can always kind of just like check yourself. So that would be 4s. 2 of them, but we need to get to zinc. So now scantium, this is where things get weird with the D block, all right, because scantium is not 4D. What is it? 3D, all right? So the periods kind of get a little bit iffy. I like to remember that hydrogen is 1s, boron is 2p. It starts at 2p, and then you like count like just numerically down, and then scantium starts at 3D. And then what would cerium? Cerium starts the F block. That would be 4F. So it's like 1, 2, 3, 4. That's how I remember it. Okay. And it comes with practice. All right. So we have 3D, and then how many electrons do we put in there? How many? 10. Very good. All right. So there we go. So there's a bunch of them. Oh, and then let's do the noble gas configuration. So you look at zinc and you just kind of work backwards. Our checkpoint is what noble gas? Argon. And so that takes care of all of up to there, so up to the 3p. So this would be argon, 4s2, 3d10. All right. All of this information is on the periodic table. All right. So let's keep going. Is this person, did they turn off their thing yet? No, they didn't. All right, so, I should note here, so some of these elements have anomalous, or what we say, exceptions to just using the periodic table to get electron configurations. There are some exceptions. And so the exceptions, all of them involve D block metals. So like when we were naming elements, D block metals, transition metals, they mess up everything. All right, those are where all the exceptions lie, and it's no different here for electron configurations. For what we call the main group elements, the S and P block, you can get all of those electron configurations just straight off of the periodic table. You look at the group numbers, it's great. But for D block elements, it's a little bit different. All right, there's two exceptions. Basically, the electron configuration for some of the D block metals is favored. The more favorable electron configuration is when you can make a half-filled D block, so having 5 electrons within your D shell, or if you completely fill your D block, so having 10 electrons in your D shell. So what I mean by that, so these are the two exceptions, where a S1, so we're essentially pulling an electron from our s orbital and placing it in the d orbital instead, because we want to have a completely filled d or a half-filled d. So those configurations are favored over, let's say, having 2 electrons in our s orbital and 9 electrons in our d orbital. See how the number of electrons are still the same? We just we plucked one off of our s orbital and placed it in the d, so that whole block is filled. Do you see how both examples have 11 electrons? All right, we just kind of spaced them out a little bit differently, and it's energetically more favorable. It's more stable there. So for our other example here, S1 D5 is favored over S2 D4. Again, you're just plucking an electron off your s orbital and putting it in your d instead. So you have a half-filled orbital, and we see a lot of stability there. And so those exceptions are here. So chromium does it, and copper does it. All right, so what you would expect for chromium, if you just did like what we were doing off of the periodic table and you go through everything, you would get 4s2, 3d4, because chromium is the 4th element into the D block. But again, like I said, we get a lot more stability if we half fill that D shell. So we're going to just take one of the s electrons and just drop it into the D, so it's half filled. And so what you actually find for chromium is exactly what we said, that half-filled D shell and actually a half-filled S shell. And so that's nice and stable. All right, and so chromium does it, and also you see it for molybdenum, but not tungsten. Why would you think molybdenum does it? It's in the same group. It's in the same group, yeah, so its electron configuration is very similar. It's just, one period down. So molybdenum does the same exact thing, right? And then for copper, same exact thing. If you go through our regular, process, you get 4s2, 3d9. But again, it's more stable if you just pluck off one of those electrons off the s and put it into your d shell. And so there it is, 4s1, 3d10. So either you can just memorize those, or recognize that there is a reason for these exceptions, and it's enhanced stability. So there's a reason for it. So you don't have to just memorize it. There's a reason for it's either having a half-filled D shell or a fully filled D shell. That's how we get that enhanced stability. And it tells us a little bit about some of the predicted charges when we make ions from these kind of anomalous electron configurations that we have. Okay, did this person mute themselves? I think they did. Okay, so how else can we represent electrons? So we're placing them in orbitals. And we already kind of talked about this, putting orbitals in a box. So each of those boxes represents an orbital in a certain orientation, 2 electrons in each box. We fill those boxes fully before we start putting them in other boxes. That's Aufbau's principle. All right. So other ways we can talk about electron configurations is in terms of, okay, how many electrons are in those boxes? Are they paired? Are they spin paired, meaning one spin up, one spin down? Or are they singly paired, right? So here, for lithium, we could write the electron configuration, 2 electrons in our 1s, 1 electron in our 2s. So what we call this lonely electron that doesn't have a spin partner, we call that an unpaired electron. And that gives lithium some magnetic properties that we can actually measure. All right, and we can relate it to the idea that we have an unpaired electron in an orbital versus paired within our 1s shell within there. So let's use that idea and look at these questions. How many unpaired electrons does a nitrogen atom have? So our first kind of idea and strategy here is let's write out the electron configuration 2 first so we know where to put electrons, right? So nitrogen is 1s2, 2s2, 2p3, 2p3. So how we would draw this in terms of its electron diagram, that's our 1s. If I draw my 2s, how many boxes are there? Our 2s orbital, is it 1 box? Just 1 box, yep. Our 2p orbital is how many boxes? 3, very good. 2 electrons in each box. So 1, 2, and that's our 2s, here's our 2p. 1, 2, and then our 2p3. So 3 electrons there. So 1, 2, 3. And that is maximizing Hund's rule. So if you drew something like this, then that's wrong. And you'd get the wrong answer. All right, so inspecting this, how many unpaired electrons does nitrogen have? 3. What? Okay, yeah, 3. So I think if you read this question too fast and didn't understand that electron configurations is related to the idea of orbitals, then you might put 7, right? Because there's 5. You might say 5 because there's 5 valence electrons on nitrogen, which we'll talk about in the next coming slides. All right, but it's 3 in this case, and you really have to draw it out. You have to draw them out and follow all of our rules within there. So then my question is here, do you have to draw the entire electron configuration to write this question? No, you can also use the condensed electron configuration. So it's helium, 2s2, 2p3. All right, so any electrons, unpaired electrons, are going to happen in not completely filled orbitals. So you can ignore your 1s orbital, because that's completely filled. That's in your inner core. It's completely filled, so it's not going to have any unpaired electrons within there. So in this case, I have a pretty light element. It's nitrogen. But what if I asked you, how many unpaired electrons are in cesium? Cesium has 55 electrons. Ooh, I don't want to draw that many arrows. But you don't have to, right? You don't have to. What is the shorthand noble gas electron configuration for cesium? It would be krypton 1, 2, 3, 4, 5, 6s1, right? So you don't have to draw any of the electrons for the krypton, that checkpoint, because all of those are paired. So for cesium, all you would have to write is that 6s1 electron, just one of them spin up. That's it. And so it would have 1 unpaired electron there. All right, so let's do, let's identify all the neutral elements that have 2 unpaired electrons in their 5p subshell. So 2 unpaired electrons in their 5p. So p orbitals have 3 boxes. Okay, so each of these are 5p. So we'll just do one of them first. So I'll put 1 electron in there. Is that 2 unpaired electrons? No, it's just 1. So there's 2 unpaired electrons in a 5p orbital. So to me, this looks like 5p2. What element has that within its electron configuration? It's the second element into the 5p block there. So it's 2, 3, 4, 5, so it'd be tin. The second element into 5p, so it'd be tin. Do we see that? Did I count right? 2, 3, 4, 5. Yeah, 5. We see that? So 2 unpaired electrons. So to me, that's saying 5p, 2 electrons in it. And I'm assuming everything before it is filled. But here's the trick. There's also another one. There's also another one. So I can put 2 electrons in my 5p shell, but I can continue putting in electrons. So that has 3 unpaired electrons. But if I put in a 4th electron, there we go. Does that have 2 unpaired electrons in it? Yes, it does, unfortunately. So what element is that? Te, it would be tellurium. So this is the 5p4, superscript 4, so the 4th element into that 5p subshell. So there's 2 of them. All right, so let's keep going. Let's skip that question because we have like 2 slides left and 4 minutes. So that whole idea of, hey, we can look at just kind of the last electrons, because the last electrons we place, are they the most stable electrons or the least stable electrons? Least stable. They have the highest energy. So the highest energy electrons are always the ones that are involved in chemical reactions, in chemical reactivity. So those highest energy electrons we actually call valence electrons. All right, so we're kind of that's like a hint into the next slides. Valence electrons, it's the reason why elements behave the way they do. These are the electrons that are highest in energy. Usually, like 9 times out of 10, it's all of the electrons that are in the highest N level are your valence electrons. If you write out your electron configuration, you can count how many electrons there are. So for example, for a lot of the main group elements like your S and your P block, the number of valence electrons is actually your group number. Right, so let's look at it. So magnesium here, that's your electron configuration for magnesium. How many highest level electrons are there? 2. There's just 2. What group is magnesium in? 2A. Okay, let's do the next one. Carbon, how many highest energy electrons are there? 4. What group is carbon in? 4A. Right? Tin. So this is when things get heavy, it's a little bit different. So tin. Here's the electron configuration. You only count electrons that are in the highest N. So you count your 5s. Do you count 4d? No, because it's lower. But you also count 5p2. So how many valence electrons? What? 4. Okay, what group is tin in? It's in 4A. And then, so just guess with me, how many valence electrons are in aluminum? 3. How about gallium? 3. Wait, is it? Yeah, 3. All right, and with gallium, you have a completely filled 3D, so that's why those 3D electrons don't count. All right, so the last slide here, finally enough time, is valence electrons, but for transition metals. See, transition metals, they screw up everything. Okay, so for transition metals, for the ones that are kind of early in the D block, you do count their D electrons. Okay, so I told you for gallium, you don't count those D electrons because it's a main group element. But if I'm talking about like scantium or scantium or titanium, you do count those electrons in their valence electron count because the energy levels between the 4s and the 3d are very close. So we still consider them high energy electrons. So in this example, scantium, we count the 3d electrons. So how many valence electrons are there? 3. And the reasoning We know this is because we oftentimes see scandium 3 plus cations. That scandium ion will lose all of its electrons. So we know that those D electrons are actually high energy. So if we do chromium here, so I didn't write it out. So chromium is argon, 4s2, 3d what? 1, 2, 3, 4 of them. Oh, sorry, but this is a anomalous one. So 4s1, 3d5. So chromium has how many valence electrons? 6. Yes, has 6. We oftentimes see chromium 6 cations out there, right? Oh, I ran out of time. And I have half a slide left. Okay, but it's fine. So I will finish this slide on Wednesday, and we'll do midterm 2 review stuff on Wednesday.